Hi, Anthony. Sorry to not get back to you last night on this. I wanted to make you a little video just explaining some of the stuff that we were talking about at the end of yesterday's session in terms of three space or three-dimensional space and the equations of lines and planes. And so I'm going to try to sort of give you a little summary here of everything that you need to know for all the different forms, okay? We're going to start with the equations of lines in three space, or R3, and what you need for the equation of a line in R3 is you're going to need a direction vector, and you're going to need another vector on the line, okay? Sorry, you're going to need another point on the plane. Point on the line. I said plane. Not off to a good start, are we? Okay. So if you have those two pieces of information, you can tell a vector, because a vector is going to have the square brackets, from a line, which is going to have the round brackets. And because we're in R3, you're going to have an X and a Y and a Z coordinate for each of those, okay? When you get those, there are three different forms that you can write the equation of a line in three space in. The first is the scalar equation. Your prof might call this something different. There are two or three other names out there for the scalar equation, but that's what I like to call it. And the scalar equation is going to take the form ax plus by plus cz plus d equals 0. When you have the scalar equation, vector a, b, c is your normal vector. That's a vector that is perpendicular to your line. Okay, that's what normal means. It says 90 degrees. And point x, y, z is a point on the line. So you can see that if you have the information a, b, c from the normal vector, and you have information about a point that's on the line x, y, z, you can easily substitute those into your equation and solve for d, and then you've got the equation of the line in scalar form. One of the really useful things about having an equation of a line in scalar form is that you can just read the coordinates of the normal vector right from the equation. So you always have a vector that's perpendicular to your line, okay? Another form of a line in three space is what we call a vector equation. And a vector equation takes a little bit of a different approach. The vector equation, let's call it vector t, is going to have part point and part direction vector. And so I'm going to put an N in there, sorry. Okay. So what you're going to do there is for any vector equation, you're going to end up with the coordinates of a point, and then you're going to have the coordinates of a vector times a parameter t. And so that really gives you sort of a family of lines. Because t can change, it means that you can have any number of equations of lines that will satisfy those two conditions. As soon as you figure out t, as soon as you fill in t, you make it one specific line. And then that kind of leads us into the third equation, which is the parametric equation that we were talking about. And the parametric equation is really just another way of writing the vector equation. You're taking the same information. Your x term is going to be just the x from here times the x naught t. So we'll have t times x naught for just taking the x terms out of those two brackets and including the t in the second term. The y is going to be the same idea, whatever the constant y is from this point, plus, sorry, I said y, t times y. And for z, we're going to have the z coordinate plus t times z. When you know t, it makes it a lot easier to write your parametric equation. And what you were referring to yesterday about pairing them up is, I think what you're doing there is you're trying to see if there's a point of intersection between a line and a plane. So I think you're a little bit further ahead from there, from just finding the equations of the lines right now. I think when you're trying to solve for t, you're actually trying to find a point of intersection between two lines or between a plane and a line. So let's switch gears a little bit. Those are the three forms of a line in three-dimensional space. So if they ask you for one or the other of those, that's how you find those equations. For a plane, it's a little bit different, and I'm just going to switch slides and show you what I mean by that. So for equations of planes, obviously that I didn't write in R3 because you can only have a plane in R3 in three-dimensional space. It's a little bit different, but very, very similar to finding the equation of a line in R3. The equation of a plane in R3 requires that you have two vectors that are parallel, two vectors that aren't parallel to each other, as well as a point on the plane. And so that's a big difference because when we did the line, we only had 1 point and one vector required. Now you need 1 point along with two vectors, and those two vectors cannot be parallel, okay? And so basically you're going to have a point, which is any vector given to you on that, any point given to you that's on that plane, plus, and we're going to have t times any position vector, let's call it A1, A2, A3, plus another scalar s times a different position vector, direction vector B1, B2, and B3. So the difference is when we had the line, the equation of the line, we didn't include this part of the equation. This is what's new here, this last part. That is an S and not a 5, sorry. As long as we have these two vectors, as well as a point on the plane, then now we've got the equation for a plane rather than a line. So you can see the difference, that there's three components to this equation and there was only two components to the line equation. Now we can easily move into vector form for this because x is going to be x naught plus t times a1, which is the x position in this vector, plus s times b1, which is the x position in this vector. And then you're going to go down like that and create your parametric equation for this plane. So we can do that really easily and change back and forth. What we can't do very easily is find the scalar equation for the plane because it doesn't translate back and forth between the vector equation and the parametric equation. So these t and s values, they're just scalar values. They're just going to be a number that when we multiply by whatever's in this vector and this vector, we're going to end up coming out with a new value that defines the equation of a specific plane in R3. If you have two position vectors, two direction vectors here, your normal vector will be perpendicular. So if you take the cross product of those two vectors, you'll get a normal vector. And that normal vector will then help you write the other form of the equation for your plane, because you can do your ax plus by plus cz plus d equals 0 using the values from your normal vector, which would be the cross product of this vector and this vector if they're both non-parallel direction vectors on your plane. So taking the cross product of those will give you a normal vector to this plane, which you can then use for ABC in your scalar equation for your equation of your plane, and you would just have to solve for D. I hope that helps. It's a little bit complicated. There's some really good stuff if you go to Khan Academy. That's khanacademy.org, and search for equations of lines in R3 or equations of planes in R3, and he will progressively take you through more and more complicated topics on equations of lines and planes and their intersections. So that's a really good place to start and watch a short video there.